So the time is hey everyone, welcome to one of the first talks for today. And today we will talk about a few words that are popular: multi-cluster, multi-tenancy, GPUs, AI research, and all those things combined. So to cover what we are covering today, so we are covering a couple of two areas. First is how and why GPU allocation is working, and second is whenever you deploy a lot of clusters, how do you achieve multi-tenancy. So those are the two components we are covering today, starting from GPU allocation, like time sharing and all those different areas, including Kai scheduler, to whenever you decide about multi-tenancy, how do you do that, and what are the best solutions on doing that. So a bit about me. I just went and clicked this picture yesterday. So I'm Hrittik, and you can connect with me with Hrittik here anywhere on socials. I'm a platform advocate at vCluster and a CNCF ambassador. So I come a lot from the CNCF ecosystem, and this is my second talk at the Open Infra community. And I've done a couple of certifications in Kubernetes ecosystem and a Google Scholar as well. So when we talk about AI, GPUs and all, one trend we are seeing is like the AI use cases are increasing. Like now we have agentic AI, real-time AI agents, AI native apps, and AI, all so many things AI. But as the use cases are increasing, we need to understand that the GPU demand is also increasing, because all of those use cases like autonomous decision systems and the AI systems, everyone requires some type of AI connection, like during inference, during training, during fine-tuning, somewhere and another part there is a requirement for GPU demand. And why is that GPUs are so popular? Like CPU can do a lot of compute. This breaks down to how GPUs are structured. So GPUs are structured to have a lot of ALUs, and in CPU the thing is like there is a lot of control logic units, so which helps you to decide, and there is preemption of tasks. So a task can start and stop whenever you want, depending on the scheduling algorithm. But in GPUs that is not the case. Mostly there is no interrupts, new presumptions over there. So whenever there is a task, it's meant to be scheduled together so that it can receive all of the ALUs together so that they can do specific vector calculations. And this is the advantage of GPU, because you can get a more throughput. But again, when you compare with CPUs, the problem is like you can't have the preemption. So whenever we talk about Kubernetes and GPUs, you see whenever there is a Kubernetes cluster, there are a couple of states whenever you are building an LLM or any AI model. Starting from the develop, training, deploy, serve, and monitor. And all those use cases can be done with a distributed system like Kubernetes. And that is one of the reasons whenever we talk about AI infra, there is a appearance of Kubernetes in all those big companies. Because like companies like OpenAI, Hugging Face, CERN, NVIDIA, Bloomberg, everyone is using Kubernetes in a way so that they can serve their models. And one more thing we need to understand is like as those models are increasing, the amount of nodes, the amount of compute, the amount of parallel processing happening together is increasing as well. So you get nodes, 7,500 nodes cluster 3-4 years back, and now the capacity is increasing parallelly as more and more use cases are coming together. So how does this GPU thingy work with Kubernetes? So whenever you want to focus on GPU and all, specifically the NVIDIA GPUs, we see there is a layer, and the reason there is a layer is because GPU scheduling doesn't happen in kernel level. So CPU scheduling happens mostly on the kernel level, but in GPU there is a stack. So there is the NVIDIA device learning stack, then the container toolkit driver and the GPU. The GPU is the real hardware, then the driver helps you talk with the GPUs. And the device plugin tells you that GPU can be used and which GPUs can be used, and the container writing times or the container toolkit is there to schedule all those things and ensure the container is running with the GPU once it's scheduled. So if you break it down, so there is the host level components, which is the container toolkit and the GPU driver, and then there is the Kubernetes component, which helps you with scheduling and all those area. And if we just focus on the Kubernetes components, so whenever we require GPU, there is a driver access, actual libraries, and CUDA, and all those things together. So whenever there is a GPU requirement, what happens is like when you launch a Kubernetes workload or any container workload, by design it's meant to be secluded. It's whenever you launch a container, it's not meant to that you will go and escape it. And GPUs are host level files and all the systems. So there needs to be a layer which talks with your host and tells that we want this hardware level access to be given to our containers. And this performance of control breach is happening through these steps where the GPU device is mounted, then the NVIDIA driver libraries are connected through the host. The injection of environment variable happens, and at the end the device C group is connected so that your actual container can consume the GPU. So whenever everything is set up in the background, your developers come and process that we want to use a GPU. It's as simple as connecting a limit and adding that stack. But in background, what happens is a complete 7-step process. So the scheduler, whichever you are using, maybe your Kubernetes default scheduler, it sees that there is a GPU number, and then what happens is like a node that advertises that there is a GPU is connected over there. And once that happens, a pod of the node is enabled, and then it's scheduled including the normal scheduling algorithms. And the kubelet on the node receives the pod specification. Once the pod specifications are received, the NVIDIA device plugin is pulled in, and then the GPU is mounted, and then operations are resumed. But this on a surface level is just a one line, but in background, once you have configured, this is the entire process that happens. And once you see what happens, then you need to understand why the NVIDIA GPU operator is so powerful. Because at the end, CPU scheduling happens on your kernel level, but GPU scheduling happens outside of kernel. So yeah, so over here, and as you see, the NVIDIA GPU operator helps you to manage the life cycle and enable CUDA and all those operations. And the container toolkit and drive containers are there so that all the operations are running seamlessly. So apart from that, there is a lot more advantages that helps you, but at the end you require it for to run all the operations that are there. Yeah. So now, as you have some GPUs running with your container application because you have configured all those steps, then we can focus on issues what arises whenever you are focusing on GPU with Kubernetes. So LLMs are expensive to run because it takes a lot of parallel processing to do that. And for big LLMs, the production time is reduced because a scheduling task is running for 1 second or more. So it is kind of locked to one task. So if we look at the inference process of LLMs, so one after one task is happening, but the problem is it's locked. And the other costs stuff with the GPUs is it's expensive. So whenever there is an ideal GPU, which is a lot of cases, what happens is like your applications are running smoothly, but as you see, there is amount of GPU that is idling, and that is not a good case when you are paying so much for your GPUs that you want your GPUs to be idled. So over here some data points which you can go through. But this was a very big problem. Then what happened was like a lot more new things came up into the market, and smaller ways like time slicing and all those stuff came together. But again, the problem with time slicing is like it looks good, you can assign a lot of things, but the actual problem is it is actually not helping you to do parallel processing because the GPU has stacked and one process after one process is scheduled over there. So yeah. Okay, later. and that is the issue. And then there are other frameworks and other things that are coming together, which we will go through one after one. It's like MPS. So when MPS comes in, so you can share your GPU at multi-point, and that is good because you can concurrently process a lot more things. But problems like data isolation is there. So if you are using a secure data set or something that you don't want to share with another tenants on your system, that is the issue which is kept over there. Then NVIDIA released MIG a couple of years back, which was released with A100s. And what it does is like it breaks the GPU into smaller instances, and Kubernetes then uses them to run each of the tasks. So suppose you have 7 tasks running. Some are inference tasks, some are fine tuning, some are pre-tuning, some are just benchmarking. You can assign one of the GPUs for each. But again, the problem with MIG is, it's good that you can do that, you can break it down, but it's very expensive as a GPU. You can buy P4s or something like that and then use it and get more performance. So the way MIG uses is like they have a lot of they have a lot of I think the diagram is old. Yeah. So it can be only segregated in 7 because each of them has a specific requirement, and then you can do everything over here as required. So some part of your GPUs can be used in certain sectors and the other parts can be used in certain sectors. So you get a complete overview of all the sectors. But with all those things, there are a couple of more questions that come into the picture. So how do you prevent one workload from monopolizing the GPU? So with all those algorithms, the thing is they help you schedule, but they don't enforce anything. So suppose a GPU, for example, a simple container is consuming an entire task because it's overbooked, then other tasks have to stop because it is not, all those things don't enforce it, but actually just promote it. And then other questions like how do you ensure fair scheduling without kernel support, and what about the security boundaries? Because a lot of data tends to stay in the hardware layer, so how do you enforce that? So those are the questions that are always up. And then if we go back and look how the overall diagram looks over here. So generally, if we go into the basic format, so there is your bare metal Kubernetes or normal cloud Kubernetes, and each of your GPU node is consumed by one single container. Then you enable a lot of time sharing and all those things, and the advantage is that you are getting the most out of it, but there can be done something more. So with something more, there is a software defined sharing, Kai scheduler, that is very popular, and the advantage over MIG is that with MIG, you have 7 equal instances, but over here you can have flexible packing. Suppose you have 10 gigabits of GPU, so you can have 2, 4, 8, all those things at all. And then it is optimized for fractional sharing. So you optimize your GPU scheduling with AI/ML workloads, and the advantage is like you can have dynamic GPU allocation as your tasks are operating throughout the whole AI life cycle. So as you see, it sits beside your GPU operator, and the main task of this is to infuse high throughput of the containers, and whenever there is interactive job that requires minimal scheduling and more throughput, you can do that using this scheduler. So now as we are seeing the different way of scheduling a simple application, a simple container on Kubernetes or normal hardware, we want to understand the enterprise component, what comes into the picture. So whenever you have a Kubernetes cluster and you are building it, there are a couple of things you want to be infusing over there. So first is most of the times auto scaling. So whenever you have a private cloud, that becomes a challenge because you can have a specific number of requirements for each tenant. but then you can have bursting as well, so you can move your workloads to the cloud when there is not enough resources over there. Then is observability, because you want to observe everything is happening, including when you are consuming GPU perform and the performance benchmarks. Then hybrid deployments are a very new, but not a new concept, but a very soon to be growing concept, where you do bursting. So cloud bursting, if you are unaware, is the process where if you have private instances or cloud instances, whenever there is peak traffic, you can move some of the instances traffic to your cloud. So you optimize and use all of your hardware in the local network and then go to cloud whenever there is a requirement. And the fourth part is CRD isolation. So even if you have a lot of GPUs together in a stack, which you will see in a moment, your teams can be many which are consuming a single cluster. So what you can do is you can give them a namespace each, but the problem is you don't get CRD isolations and all those things. So that becomes a challenge, because whenever your team is building some custom resources, they want to be having full autonomy of that cluster. But that becomes a challenge over here as we are using simple solutions like namespaces. And the last was GPU access and distribution. You want to be having a fair usage and distribution across all of your clusters. And then security and audit. So it is not just on the infra team layer, but as well as compliance layer, where you are enforcing all of those things. So those are a couple of simple requirements whenever you are building a Kubernetes system. But those go beyond this. I just put in a couple of them. So if we see how we create a cluster with this, a GPU cluster. So generally, the simplest form is you have two tenants, tenant A and tenant B, each divided between your business unit if your revenue sector is connected through that, or team unit if that is something your company is architected across. So each of them have GPUs. Each of them are scheduling something with that, but the problem is that having low utilization is wasting money on the table, and again having high utilization is also not good. So there might be a middle ground where you are utilizing it in a better way. So people came with a smarter technique where they remove the business units and create a big cluster overall, and each of them GPUs are consumed in a better way. But the problem with this is whenever there is a lot of resources, there are isolation and security problems, because the applications running inside your host cluster, which is shared across your different tenants, the RBACs at the first problem, and the second problem is custom resource definition, because each of your team tenants are running different custom resources, and you want them to be having that freedom of using whatever they want instead of bundled across a single version across all of your teams. So here what vCluster comes in. So whenever vCluster comes in, what it does is like it creates a virtual cluster on top of your host cluster, and you can have n number of virtual clusters. So by virtual, I mean those are real clusters, and what we do is like we create an API server on top of your host cluster, and that's the API server is the point of our contact between different hosts and different teams. So for example, if you have 10 business units, you can have a single host cluster, and then each of your business unit can have a virtual cluster which is extension of your host. So the advantage over here is now you can have the same architecture as before, but you get the benefit of isolation over here. So each of your virtual cluster that has been created can have individual CRTs, individual access for the business unit or developers, while your infra team is consuming everything through the host, and your GPUs have a better utilization. But next is like sometimes you have different kind of GPUs. You don't want each of your teams to consuming the best GPUs you have. For example, if you are just running some performance benchmarks for your models, you can do that in a T4 or smaller GPU. But if you are running a huge inference task, you might need powerful GPUs, right? Like all workloads are not created similar. Like that, it's possible to label the requirements for each of the GPUs and use that with vCluster. And the third most important thing is like whenever you have a lot of cluster and a lot of things, you want to optimize it for cost as well. There are a lot of neo clouds right now which sells the GPUs in a cheaper rate in comparison to your whole Kubernetes ecosystem rates, where like for example AKS, EKS have GPUs which are quite costly. So there is that difference as well. So with private nodes, what you can do is like you can have a specific GPU stack from a specific infrastructure provider. So the advantage is you can consume those without positioning it in a way. So overall, we talked about a lot of things, but what does sharing GPUs and sharing a host gives you? So in a simple use case, it's very good that you can share and all those things. But actually when you architect your entire system, those are a couple of use cases you combine. So first is multi-use case inference. Suppose you have an AI cluster with a couple of different type of inference tasks happening. So you can do that, like one inference and second inference, third inference, all of those things are combined and running together. Second is GPU as a service. So whenever you're creating a private cloud, for example, inside your company, you want your GPUs to be distributed in an even way or in a way that is required by your teams. So previously when you share your GPU, the problem was like you need to share the isolation unit as well. That is most of the times not possible. So over here you can have different tenants which are consuming your GPUs simply. Then other use cases like those on that front are like AI cluster with multifunctional use case. As you see, there is inference, is fine-tuning, pre-tuning, everything is running together over here. And then there's a class of distributed inference as well. So in distributed inference, you can inference your remote sites and all those things together. So overall, what vCluster provides you is it lays integration across your different teams so that you can have throughput which is high and accessibility as well. So whenever there is a requirement for a specific team to go and access a simple cluster, you don't need to run through your IT teams to go and create an entire cluster with more GPU stack. What you can do is just go and create a simple virtual cluster unit which will have all those hardware level requirements at first, and then your teams can consume it. So in conclusion, so with the GPU integration and vCluster, what you get is like fully isolated units including CRDs for your workloads. And then there is a control plane cost saving component as well. So with open source vCluster, what you get is like whenever you are creating a EKS cluster, you pay a number of dollars, $80 per month for each control plane. But as the number of clusters increases, apart from your GPU cost, the cluster cost for your control plane is also increasing. So when you have a simple host cluster with a lot of virtual clusters on top of that, which have virtualized API server, you are not creating a new API server for each of the units. You are just consuming the virtual API servers. So for one single EKS cluster, you only pay once, and your different business unit can consume that virtual clusters easily. Last is better optimization for GPU sharing. Traditional ways only focus on sharing the GPU without caring about the data risk and the data being there whenever there is MPS. So with this, you can, with Kai and vCluster, you can have a where your Kai is focusing on sharing the data and your vCluster is isolating the control units so that your each team can consume it in a efficient way. So that is all for my talk, and you can join in the vCluster community if you have any questions when you're trying it out. And vCluster is quite open source, so you can try it at vcluster.sh and run it on your any Kubernetes cluster. And I'm opening the floor for any questions as we have few minutes. Sure.
I was wondering, why do you need to, because the original use case was to provide GPU access to, let's say, different teams, so they don't overlap between each other. Why can't you do that by using just the quota of the resource quota use resources from Kubernetes, because, for example, you can say that, hey, for this namespace with CPU or with memory, you cannot use more than this certain amount of CPU or memory. So can't you do that with the fractional GPUs?
Oh, like, so if I understood your question is like, why can't we use resource quota on GPU,
Yes.
right? So how GPUs are structured is like, when you implement Kai and all, then you can share the specific GPU. But overall, you by default you schedule it on a single GPU. So when you have a single GPU, that becomes hard.
Okay, so if you have, let's say, two pods requesting 0.5 GPU, when what they do is that they cannot access the same GPU at the same time. They have to wait one for the other.
Yeah, that is the task. But again, you can't by default without Kai or anything. You can't request a 0.5 GPU.
No, I know. Yeah. But one after you have Kai, why can't you use the quota mechanism of Kubernetes to lock the consumption of the consumption for
Another thing
the
is,
same time?
so GPU scheduling over there, it's it's not enforced, by the way. So if a task is consuming more,
Oh, okay.
then your next task can't be scheduled. So currently there is nothing that can be enforced apart from MIG.
But if you use the request instead of the limits, doesn't that allow you to?
Like last time I checked, you can't.
Okay.
Yeah, for GPU specific. For memory and all, it is very possible.
Because I know that for CPU it works like
Yeah,
that way.
for CPU and all those are. But
Okay.
the thing what happens is like GPU scheduling happens not on the kernel level. It happens
Okay.
on
Okay.
the device level. So those kernel benefits we can't consume over here.
Okay.
Yeah, please.
To use the NVIDIA features you presented, or also the vCluster, do I need an NVIDIA license, like the license?
No, those were open source.
Yeah, but to use the NVIDIA features, I don't need some license from NVIDIA.
No.
NVIDIA operator, you don't need.
If you use possible for me,
You don't need a license, right?
only for VGPs.
Thank you.
Yeah, please.
Did you guys have any experience with larger scale, like superpod architecture from NVIDIA, where also the
Yes.
Yes, or DGX and superpod, when there are a couple of dozens of these. Have you been trying maybe vCluster?
Yeah, we are trying with DGX.
Okay. But in the InfiniBand as well and stuff like that?
Yeah.
Okay.
So there's Netflix.
Yeah, the network operator is
Yeah.
important there.
Yeah. So we are on that process of benchmarking all those things. So if you want,
Yeah, I would be happy to see, because we have such an issue right now.
yeah, because we are just operating with DGX, but DGX are expensive. So yeah, we are working some areas over there. I would like to connect with
Yeah, I would
you.
jump in the Slack.
Yeah. Sure. Thank you so much for joining in.